All right, so fragmentation patterns. So now let's look at the mass spectrum of alkanes. So here is a given compound. We have hexane. So the molecular mass is the MZ value is 86, right? So basically, fragmentation in alkane can occur at any point. It's important to note that. So and because it's not, this particular compound is not branched, so we can have fragmentation here, we can have it here, we can have it here, we can have it here, or any point. So when you, the first thing that happens that when you bombard the molecule with high energy electron, you have the molecular ion peak, right? You have the n plus dot. So that's what we observe here. So the next thing is that we have 71. So how do you have 71? You have simply 86 minus 71. That will give you 15, right? So that's n plus minus 15, or simply n plus minus CH3. So that's what we have here. So when you remove when you you break this, you fragment this part, you are expected to have let's put it here. That will be CH3, CH2, 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 right? So positive, and then you have CH3 radical. So this one here is a priming carbon. This one, well, we don't need that one for here, for this point. So here we have, this one is just a priming, this one is secondary, this one is secondary, this one is secondary, this one is secondary, and this one is primary. So basically the most stable fragment that will be obtained is when we fragment between 2 2. So but it will be nice if we fragment it here. That's more more linkage here, and that's more linkage here than when we fragment it here. Okay, we can also fragment it here. So let's see, basically when we fragment here, we add this. So when we fragment here, we're going to have CH3, CH2, 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 right? Positive plus CH2, CH3 radical. So this is minus 20, this is 15, this is 14, so minus 29, right? So that should give us this 57, m minus 29. This one will give us this 57 here. So this is the base peak, it is the most intense, and it is actually because the molecular ion here has the carbocation rather, and carbocation here has more first of all, it's between 2 2, not between 2 and 1. It's more stable than any other one we can produce actually. So if we try to look at this, basically let's say we fragment. Okay, we've done this. So let's say we fragment here, right? So we're going to have CH3, CH2, CH2, right? And plus we're also going to have CH2, CH2, CH3. So any of them can be the positive radical, but looking at the length of this, they are both 2 2, right? They are between 2 2, but the length of this is 1 2 3 4, 1 2 3. So this is more stable. So we have this to be the highest peak. So you can be given a question, give the fragmentation pattern of n hexane that correspond to n plus minus 25. Is it 25? No, I think I wanted to say minus 29. N plus minus 29. And that's what we just add here. So that's what we add here. So just write it out, what we add here, and then give it to them. So the fragmentation pattern, you can just draw the structure, write the structure out, indicate this fragmentation, and then you write this fragment out, and then you now write it m minus 29 or m minus or m plus minus CH2 CH3 basically. So that's that. So let's see another fragmentation. So let's say we have 2 methylpentane. So the fragmentation of branched alkane commonly occurs at the branched carbon. So pentane is 1, 2, 3, 4, 5. So we have 2 methyl, right? CH3. So this one is CH3. So this one is H, and H. So this one is H, and this one is let's just put it CH3, right? So looking at this one is 1 degree carbon. This one is bonded to 1, 2, and 3. So this one is 3 degree carbon. This one is bonded to 1 and 2. So this one is 2 degree. So this one is bonded to 2 degree, and this one is 1 degree. Now, the most stable fragment, first of all, recognize or acknowledge the fact that fragmentation can occur at any point. It can occur here, can occur here, any point. But the most stable carbocation, the most stable fragment will occur between 3 and 2. So if you fragment here, and you give this point positive, this point negative, so this will be more stable than this one actually. So this fragment CH3, CH3, hydrogen plus C, H, C, H, and CH3, and this given as radical. So this will be the more stable. So right. So let's look at this other example. So fragmentation of 2,2-dimethylpropane. So 1, 2, 3. So propane, right? CH3. So this one is also CH3. This one is CH3. So first of all, identify a fact that fragmentation can occur any point, right? So this one is how many degree carbon? This one is 4 degree carbon. This one is 1 degree, 1 degree, 1 degree, 1 degree. So any point you fragment this one will give you the same stuff. So you can just say CH3, and plus this one dot CH3. So this one should give you the fragmentation pattern, right? This one should give you a more stable product. So cycloalkane, the most common fragmentation pattern in cycloalkanes are usually the loss of ethylene group, right? The loss of this group and loss of side chains. So the fragmentation of cyclohexane. So this is cyclohexane, 2, 3, 4, 5, 6, right? So fragmentation of cyclohexane. So 2 things occur. You just need to note that. So you try to know it often. Cyclohexation of hexane. The first thing we have loss of the ethylene group. So when there's loss of ethylene group, this part goes off, right? So what we are left with is this. Right? Plus this. So this is basically what we are left with. So this one becomes positive and this one becomes radical, right? So that's first one. So another thing is that if there's a side chain, there's a loss of the side chain. So let's look at these two. So cyclopentane, this is cyclopentane. So methyl-cyclopentane. So we have CH3. So the first thing that will be lost here is this methyl group to give A, which is this one. So when you lose this point here, there will be positive here, right? There will be positive here, right? Or you can let me explain it in another light for you to understand. So basically, this is the bond that is most likely going to be broken when we want to fragment, right? So when you ionize, we are going to have this. You can simply put it this way. Maybe this will help a bit. Dots plus CH3, like the bond here, you broke it down to this point when you ionize, right? So fragmentation therefore becomes this positive plus CH3, right? So that's that one. So now let's see. So once this is the first product, the second product would be the loss of ethylene group, right? So fragmentation of alkyne halide. So alkyne halide is like you having CH3, CH2, CH2, and like Cl, right? So loss of halide, that's the first thing that happens. You lose the halide, like when CH3, CH2, CH2. So when you ionize this, right? When you ionize this, you have positive dot Cl, right? Which therefore gives you CH3, CH2, CH2 positive plus Cl radical, right? So that's the first product. So another thing that happens is the loss of X group. So that is basically like you having CH3, CH2, and then you are losing this, like you are removing these, so we are going to have CH, but that is always leads to the formation of a double bond plus HCl, right? So let's just move on. Let's leave that third on. It take a lot of time. So fragmentation of alkanes, right? So let's say we have hexane, two hexane, sorry, this is hexane, not hexane. So 1, 2, 3, 4, 5, 6. So this is 2, right? So CH3. So hydrogen, 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 and CH3, right? So beta cleavage. So this is the carbon. This is the alpha carbon is attached to the carbon that contains the functional group. So this is the beta carbon, right? So let's put it that way. So the parts with the double bond usually contains the positive charge. So when you fragment, first of all, identify the fact that fragmentation can occur anywhere, can occur here, can occur here, can occur here, anywhere, or even the hydrogen bond. But when we are talking about the most stable product, the most stable product is when you fragment far away from the double bond in order for resonance to occur. Like when you fragment at this point, beta, we call it beta cleavage, because this beta carbon, this is the beta carbon, is leaving. That's what we call beta cleavage, right? So this is alpha, this is beta cleavage, because this beta carbon is leaving. So when you fragment at this point, you are going to have CH3, CH2, and plus you're going to have this double bond, CH3. There is hydrogen here, there is hydrogen here. And no, this is the fragment, this is the beta, this is the carbon, that's beta. This is the fragmentation point, so there's still one carbon here. So CH2, right? So now let's look at the part that will contain so we said that the part with the double bond usually contains the positive charge. So this one will contain positive charge, and this one will contain the radical, right? So that is that part. So let's say the bond is longer, like 7. There can be a possibility of resonance, like this bond can like resonate with the other carbons there, but that's for longer carbon chain. So now let's look at this interesting one, which is McLafferty rearrangement. So pentane is like, let's draw the structure this way. So let's say we have C2, 3, 4, 5, right? So this 2 methyl. So let's say our CH3 is here, right? So 1 pentane. So this is the double bond here. So for McLafferty rearrangement to occur, there must be alpha hydrogen. So this is the carbon that is attached to the functional group, right? So this is the alpha carbon, this is the beta carbon, this is the gamma carbon. So if you can't find a gamma carbon, then alpha rearrangement cannot occur. It does not stop there. Even if there is alpha carbon, if there is no alpha hydrogen, McLafferty rearrangement will not occur. So looking at this, this one is like 1 2, there's CH2 here, right? So this one is 1 2 3 4. So this one is a CH2, this one is CH2, and this one is CH3, which you can also write when you are dealing with McLafferty. Just write it CH2, you extend the final hydrogen out, the CH3 basically. So let's say we have something like this, double bond C H2, right? CH3, we have CH2, we have CH2, and we have this is the gamma carbon. If this one was like CH3 and hydrogen, there's still alpha hydrogen there, so McLafferty can still occur. But if this was like CH3 again, there's no alpha, there's no gamma hydrogen, so McLafferty cannot occur. Or let's say the bond length only stops at this point. Let's say this was just CH3, this is just going to be alpha and beta, so McLafferty can still not occur here. But looking at this, there's alpha hydrogen and there's gamma hydrogen, so McLafferty rearrangement can occur. So now, what do you now need to note in McLafferty rearrangement? For McLafferty rearrangement, first of all, we are building on the fragmentation pattern in alkene, right? So and the most common fragmentation pattern in alkene is the beta cleavage. So the first thing is that this bond breaks, right? So when this bond breaks, three things are occurring in McLafferty. The first one is the beta cleavage, right? Beta cleavage. The second is that the gamma hydrogen cleavage, right? And the and the third one is the migration of the double bond. So migration of the double bond, right? So this is the first one, the cleavage of this. So this one breaks. Is like when this one breaks, it's like you putting dot here. Bonds like this are always recognized as dot. This bond here is dot. Even this one, the single bond here is dot. This one is dot, right? So when this one breaks, this one goes with one dot, this one goes with one dot, right? So when this one also breaks, this one goes with one dot, this one goes with one dot. So we are left with something like this. We have CH2 dot hydrogen dot, right? So we have this one CH2 also, right? Let's use another pen. Dot. So this one is dot. Let's put this one's dot. Let's put it here. This is carbon, right? Dot. This one's dot is this. So this is this one's dot. So therefore we have the CH2 here. We have this CH2, right? So we said the migration of this double bond. So this double bond migrates here, right? So we're going to have single bond here, C, and we're going to have this one also. So this double bond migrates here. So we have this double bond here. So we have CH2. So but this CH2 has so this CH2 has a dot on it, right? So this CH2 has a dot on it, right? So this migration of double bond here, let's just assign it as dot also, like dot, please. Let's assign it as dot. Let's not put it migration of double bond. I'm just trying to put it in a way you understand. The first one is beta cleavage. This one cleaves, so we have dot, right? And that's what we have, dot here. So this one also cleaves, we have dot. That's what we have here. So this double bond also represented as dot and dot. So there's nothing here, there's no double bond here. So represented as dot, right? So there's CH3 at this point, right? So now the next thing we need to do is to join the dot. Since this one cleaves, goes this way, this one cleaves to this way, so this one is going to join, this one will join, this one will join. The direction is like this, it's like clockwise. So this one will also join with this, right? And then this one will join with this, right? So we're going to have CH2 double bond CH2 plus this structure CH2 is joined to this, so you can call it CH3 already. So we have CH3 and we have this double bond CH2. So don't worry, I'm going to explain better. Let's use a plain board like this. So what we did there was, the example was 2 methyl pentene. So 2 methyl pentene, right? So let's explain it again. So we have this structure, right? This is 2, we have this 4, and we have 5. So first of all, we'll be able to see that, let me write it out, CH3, right? So this one is CH2, this one is CH2, this one is CH2, this one is CH3, but right CH2, we extend the hydrogen here. So we are able to see that this is alpha, this is beta, and this is gamma, right? And there's gamma hydrogen there. So for McLafferty rearrangement, we are building on the alkane fragmentation pattern, which is fragmentation of the beta carbon, right? So when we fragment this, right, we are going to have dot dot. When we fragment this, we are going to have dot dot, and this one is simply as dot dot. So it's the same thing as writing this CH2. We have CH2, right, dot A, and dot A, CH2, we have C, we have CH2, right? So we have dot dot CH3, right? And this one dot, and this one dot hydrogen. So the next thing now we need to look at is this. This one has been fragmented, this one has been fragmented, and this one has been explained further. So because the direction is like this, fragmenting, fragmenting, fragmenting. So this one is going to join with this here. This one is going to join with this. This one will join with this, and this one will join with this. So we are going to have CH2 double bond CH2, right? Plus this one will be CH2 joined to hydrogen, or you can call it CH3. So this one will become single bond CH3, and this one will be CH2, right? So that's the fragmentation pattern that we have there. So just take note of this, please take note of it. So it can also be anything. McLafferty can also occur with any other thing. So now next thing we need to look at is the retro reaction. This is common for cycloalkanes, right? Alkanes, sorry, not alkanes. So when you say cycloalkane like this structure, so just know this is the pattern that goes on there. So what you need to know is that there's fragmentation here. There's also fragmentation. There's fragmentation here. We are fragmenting here rather. We are also fragmenting here, and there's migration of the bond. It's like you having, this is structure, right? This is structure. We have this. So we fragment here, fragment here. So when we fragment here, we're going to have something like this, no bond. So dot dot this. We have dot dot, because we are fragmenting this also. So therefore what next do we have? This dot and this dot joins. We have this. So this one is also like dot dot, right? It's also like dot dot. So this joins with this, and this one are joined. I don't know if you get it, but that's just a simple illustration. Like you represent, this is the bond, right? So we basically represent the dot bond as dot dot. Since this one is fragmenting, we call it dot dot, and since this one is also fragmenting, we call it dot dot. So this one joins with this one joins with this, and this one joins with this. So let's see the next stuff there. So yeah, this is very important. So fragmentation of alkyl benzene. So the first thing that happens is that this one can be fragmented out. So once this is fragmented out, this becomes like the benzene ring, right? We have the benzene ring, and we have the CH2, we have plus R dot, right? So furthermore, this one can be explained as a 7-membered ring, like a 7-membered ring. So you put this here, 7 carbon ring, right? So that's what we have here. So it now expels CH triple bond CH, like it expels C2H2, right? So it's like you having this structure here is already, this one is C6H5 joined to CH2, right? So when it comes here, it's like C7H7, right, plus, right? So when you are now removing C2H2, it's going to give you minus C2H2, and that will give you C5H5, and that's what we have here, plus okay, C5H5, right, rather, that is what we have here. So take note of this. This is very important. Just go and know the pattern, please. Know the pattern. So let's also look at this as well. So with some alkyl benzene. So now looking at this, this is McLafferty again, McLafferty rearrangement. Anytime you see like let's say you have a functional group at this point, and then you count the carbon alpha, you count the carbon beta, and you count the carbon gamma, and it has alpha hydrogen, McLafferty can occur. So looking at this structure here, basically it's still the principle of McLafferty that we've done earlier. So what you need to take note is the fact that this is the gamma carbon, this is the beta carbon, this is the alpha carbon, right? So we said the other time that this double bond becomes like something like dot, right? So this bond here is broken, and this leaves this one with point dot, right? So this bond also here is broken. This leaves this here with dot, right? Let me write it out. So this is structure benzene, right? We have benzene ring, and we have, this is the carbon CH2, and we have this one, so we see CH3. You see there's gamma hydrogen there. So this is alpha, this is beta, and this is gamma, and there's gamma hydrogen there. So this double bond, you break it out, you're going to have something like dot here. So this bond is breaking. If this bond breaks, so let's see. Okay, this double bond here breaks, right? So here again, this one breaks. This bond here breaks. There's a gap in between this one here. So this one breaks here, right? And this there's a gap here also, and this gamma hydrogen breaks, right? So just take note of this. This double bond is repeating the direction. This double bond breaks, there's a gap here. This one breaks, there's a gap here, and this one breaks here, like this. So this is the direction we're heading to. So basically this one joins with this one, right? So this one joins with this one, right? And this one joins, remember that this one will be leaving, joins with this one. So we are going to have this benzene ring. We are going to have this benzene, this benzene. Remember that this double bond has been represented with this dot, right? So, and it's joined to this already. So this one, and the other one is here. So that's CH2, right? So this bond has been broken already. So we have CH2, double bond, CH3. Sorry. so CH3 here. So also here, this one is CH3. So this bond also has been broken. So you have the hydrogen here. So that's what we have. That's what we have here. That's what we have here. Yeah, that's what we have here. So this carbon is bonded to 1, 2, 3, and another hydrogen here. So that's just that there. So, and this one is the same thing as this. So I hope you got it. So fragmentation of alkyl carbon. So basically, looking at this one, the alkyl group fragments. So when it fragments, it leaves with dots as this, and this one is left with this. So it's like this basically. This bond here breaks. So when you ionize this compound that contains O, this one contains the plus dot, right? This structure, when you ionize it, contains the one with O contains the plus dot, right? So when you now want to break this bond, this one goes with dot. Then you break this bond. This bond is simply as dot dot, and you break this bond, right? So this one goes off. So there is a dot here. It joins with this, and then you have this one. When you are ionizing stuff that contains hydrogen like this, that contains oxygen like this, it has a plus dot here. So this bond breaks and joins with this. I don't know if you got that. So the next thing is that this leaves as CO. It leaves as CO. So you need to know the pattern for it to like solve more complex questions. So when this one leaves, you have a plus here. So it extrudes, and then you have it extrudes. So anytime you have a structure like this, a benzene that contains plus here, it always leaves with C2H2. This is H5, right? Minus C2H2. That will give you C4H3 plus, right? So let's say it's even 7. Let's say it's even 7. Yeah. Let's say it's even 7. So we're still going to remove C2H2, and then you get the necessary product. So that's that. So now let's look at this final one. So fragmentation of aryl alcohol and phenols. So this one basically, the first thing you do is that you can actually, alright, so let's look at this. So this one is simply like, recall that when we add a 6-membered ring, with CH2 plus, we can write it as your 7-membered ring, right? We can write it as 7-membered ring, right? Sorry, don't mind my diagram. We can write it as 7-membered ring, right? So also here, when we have CH2OH, we can also write it as 7-membered ring that now contains OH, right? So this one leaves as we have okay, this CO therefore leaves like this is it, the 7-membered ring. All these are carbon. So CO, this C and O leaves, and then this hydrogen is joined to the ring there. So like this, CO leaves. Like basically when you have a 7-membered ring that contains OH, 7-membered ring that contains OH, it's like it's unstable, so it's going to lose one carbon with the oxygen. So then it returns back to 6-membered ring. So we can therefore have all of these actually. So you just gonna study this mechanism. Just study the mechanism actually. So now this is also phenol. So try to understand, just learn the mechanism as well. So let's see question. We're going to solve this question in the next video. Yeah.